Second lesson of lenses. In our first lesson, we looked at the introduction of lenses. Today, we are going to look at the lens formula and magnification. I hope you are keeping the SOPs that they were provided by the Ministry of Health. I'm Nicholus Busobozi to take you through this lesson. Relationship between the object distance u, the image distance v, and the focal length f of a lens. Consider a ray of light from a distant object incident on the lens as shown in figure 1. The ray is converged to the principal focus f and suffers a deviation d. From figure 1, tan d equals to h over f. D is a small angle, and when measured in radians, D is approximately equal to tan D, which equals to h over f. From figure 2, the ray from a point object O suffers the same small deviation D to give rise to a point image I. From geometry, D equals to alpha plus beta. Tan alpha equals to h over u, and tan beta equals to h over v. Alpha and beta are small angles, and when measured in radians, alpha is approximately equal to tan alpha, which is equal to h over u, and beta is approximately equal to tan beta, which is h over v. From equations 1 and 3, equation 2 becomes h over f equals to h over u plus h over v. Since h is common, we can divide it out to get 1 over f equals to 1 over u plus 1 over v, which is the lens equation or the lens formula. Similarly, the lens equation for diverging lens is 1 over f equals 1 over u plus 1 over v. So as a simple exercise, derive the lens equation stroke formula for a diverging lens. Magnification produced by a lens. Magnification is defined as the ratio of the height of image to the height of object, or it is defined as the ratio of image distance from the lens to object distance from the lens. To prove this, let us consider the figure below. Consider the formation of a real image of height h1 of an object of height h by a lens. From triangle OPH, tan theta equals to h over u. From triangle IPH1, tan theta equals to h1 over v. Equating the expressions for tan theta, we get h over u equals to h1 over v. If we rearrange it, we get v over u equals to h1 over h. So therefore, magnification m equals to image height of object height, which equals to image distance from the lens to object distance from the lens. So relationship between magnification m, image distance v, and the focal length f. Using the formula 1 over f equals 1 over u plus 1 over v, multiplying that expression through by v gives v over f equals to v over u plus v over v, but v over u equals to m. Thus, v over f equals to m plus 1. Making m the subject, we get m equals to v over f minus 1. Relationship between magnification m, object distance u, and focal length f. Still using the lens formula 1 over f equals 1 over u plus 1 over v, multiplying through by u gives u over f equals to u over u plus u over v, but m equals to v over u, thus u over v equals to 1 over m. Therefore, we get u over f equals to 1 plus 1 over m. Making 1 over m the subject, we get 1 over m equals to u over f minus 1. Lens formula for a thin lens. A thin lens may be regarded as being made up of several portions of small-angled prisms placed together as shown in the figure. All paraxel rays incident on the lens at a single point suffer a similar small deviation, d, which equals to n minus 1, a, produced by a prism of small angle a regarded to have replaced the lens. Consider a ray of light from a distant object incident on the lens as shown in figure 1. The rays converge to the focal point f and suffers a small deviation d. From the figure, tan d equals to h over f. D is a small angle and when measured in radians, d is approximately equal to tan d, which equals to h over f. From figure 2, the red dye normal to the lens surface passed through the centers of curvature C1 and C2. Thus, from geometry, A, which is the prism angle, A equals to alpha plus beta. From figure 2, we have that tan alpha equals to h over R1 and tan beta equals to h over R2. But alpha and beta are small angles, and when measured in radians, alpha is approximately equal to tan alpha, which equals to h over R1, and beta is approximately equal to tan beta, which is h over R2. Thus, our second equation becomes A equals to h over R1 plus h over R2. From the expression of deviation that d equals to n minus 1a, we substitute for d and a to get h over f equals to n minus 1 into h over R1 plus h over R2. H is common to both sides, therefore we divide out by h to get 1 over f equals to n minus 1 into 1 over R1 plus 1 over R2 as the lens equation for a thin lens. The sign conversion. When using the above expressions stroke formulae that we have derived, the sign conversions have to be put in mind. The focal length for a converging lens is positive, while the focal length of a diverging lens is negative. The object distance for real objects is positive, while the object distance for virtual objects is negative. The image distance for real images is positive, while the image distance for virtual images is negative. The radius of curvature is positive for convex surfaces and negative for concave surfaces. I've put the diagrams below to help you identify convex surfaces and concave surfaces. For more information, please visit the link below or send us an email at info@tricona.sc.ug. Thank you. Stay safe and healthy.